we are ready here. Hopefully you're also ready in person and on Zoom. It's my pleasure to introduce Curtis McCully, who is presenting Marshaling follow-up resources in the area of LSST. Please take it away.
Great, thank you so much for having me. Thanks for coming to listen. So we've heard the word TOM a few times, so I want to expand on that a little bit, give you an idea of what, say, TOMs are, some of the ways we've used them, and then how LCO specifically, LCO here being Las Cumbres Observatory, has developed tools to make it easier for everybody in the community to build their own TOM type systems. Now, much of what I'm going to show you today is not code I directly wrote, and so there's a whole variety of people who have been working on this, so I hope I do all of their work justice. So, yeah, I probably don't even need to say this, but I will anyway. As LSST turns on, there's going to be a massive number of alerts that come every night. Now, you know, Dan illustrated this really nicely, just showing some of the different brokers, but there's a bit of a disconnect between getting those automated alerts, those messages, and then being able to do science with them. You know, your picture of what the LSST light curve looks like this morning was really a good eye-opener, a good reminder of we're going to need other types of data to really do the full gambit of the science that we want to with LSST. Now, again, with all of these alerts, though, we need systems that scale. We need systems that are not limited by, say, the number of people in this room. We need things that'll scale much, much larger. And so we've been designing automated systems to do this. So first of all, just talk about what a quick definition of a TOM is, because we get this a lot, and then I'm going to say TOMs over and over throughout this talk, and I want to make sure that we're on the same page. What a TOM is it's a central database system that can do analysis, it can store your data, it can also help you trigger follow-up on a set of, say, interesting objects, interesting transients. So this system has to be designed in a way that it'll take data from the telescopes, from the alert streams, store it in some way that users can then either set up algorithms to make decisions or have enough data to make decisions rapidly themselves, and then respond to those decisions by making new observation requests and triggering follow-up. All right, so that's what a TOM is. And the reason that we've had to produce these has been Las Cumbres Observatory. Many of you may not know what Las Cumbres Observatory is, so I'll give you the standard slide with the standard map. So Las Cumbres Observatory is a network of telescopes around the globe. We operate 25 robotic telescopes, smaller apertures typically, so our apertures range from 40 centimeters up to 2 meters. Now, we have imagers on almost all of our telescopes, and we have 2 low-resolution spectrographs called Floyds, and we have 4 high-resolution spectrographs, which are mostly used for exoplanets, that are called NRES. Now, so this exists and it's operating today, and even the data flow from this is becoming unmanageable to do by hand. Andy can tell you a lot about how this is all working, but working with Las Cumbres Observatory, using the telescopes at Las Cumbres Observatory, we've been working on a major project called the Global Supernova Project. These are a couple of plots that I've pulled from recent papers from either graduate students or postdocs. And one of the things is you'll notice that these light curves look a little different than the LSST light curve that Dan showed this morning. Many filters, very high cadence, well sampled. And we also cover a large number of objects. So Jamie Burke's paper, for example, is a sample of 4, and you can look at the different sampling of these different things. Now, the coordination to get all of this data is non-trivial. Yeah. But we also don't have a very large group. Our entire group is, what, 6 people now, Andy, is that right, or 7, something like that? And we're having to manage the data collection, not just the discovery, but really the follow-up of these different objects with a very, very small team. And so as such, we built a system called the Supernova Exchange. Now this is the version 2 of the Supernova Exchange, but this is effectively what we mean by when we say TOM. So this particular page acts like a Facebook page for a given transient of your choice. Now, this happens to be 2017 CBV, which is an interesting object that we got very early data on, but it's mostly just as an example. But from this one landing page, we have a lot of information about this supernova. We have, is it observable? We have notes taken about it on why people have said this object is interesting. I don't know why the Aladdin viewer didn't populate on here, but we have archival images of the sky. We have images, our most recent data taken on this part of the supernova. And then we have our light curves, which are automatically processed and put on this plot. This plot will automatically update whenever we take new data. And we also have a page for spectra. And so from this one place, this one landing page, we can start to make decisions about what kind of science we want to do with this object. And similarly for the many other objects that we're doing, or that we're following. At any given time, the Global Supernova Project is following about 50 live supernovae. And so, over the years, that's hundreds and hundreds of supernovae that are getting this kind of attention. And that many of them will have good sampling, but perhaps not as, this is, of course, one of the best cases. So, let's kind of walk through a workflow of what this whole system would look like, what you might do if you wanted to go from some kind of transient alert to science. So this is starting, and hopefully this plays. Yes, good. So we start by ingesting an alert. We're going to use the transient name server here as just a first example. And so what this is doing, or what this page is doing, is it's going to query the transient name server for all of the recent supernovae that have been discovered and have gotten a new name. Now, you can already start to do interesting things at this level because it's all customized. You can start to filter by when's the last time there was a detection. Is this a young supernova or is it likely old? We can put brightness cuts and say, I only have, say, 40 centimeter telescopes because who knows, for whatever reason. So I only want the brightest supernovae above a certain cut. And all of that you can do right here. Now, once we found an object we're interested in, let's see if that's going to play. There we go. So say we want to filter down to an object. And actually, this is a real object that one of my graduate students, Craig Pellegrino, did today. And so we filtered down to the object that we're interested in. So we can get a little bit of information. Yeah, it's in a galaxy it's kind of off to the edge of its host. It's pretty well visible, and so we're going to say, this is going to be an interesting target we're going to follow. So now, with the click of a button, we can then add that into our TOM database. And so, we can save things like the position, the name, and importantly, we can set the permissions of who is allowed to look at the data we collect on this object. As we make our data collection more complex, our permissions are going to be more complex as well. And so we have to worry about that as well. So once he hits submit, that will create a new target in the database, and it will then store it. So we've taken an alert out of TNS. Now, this could be any other type of alert. This could be Antares, because I have to say Antares or Gotham kicks me out, right? But it doesn't matter. You take an alert stream and you turn it, and then you save it into the database. After we save it into the database, then we've got all this data. We can start collecting it and saving it in one place. And so I showed you a screenshot of this a little bit before, but I'll walk through a couple other things. One of which is, it shows the different comments that people have made. We can look at the observability. This whole system is a web-based system, and all of the plots are designed to be interactive. And so because of that, you can actually start to do analysis on the fly, even if it's basic analysis. So for example, like I can change the light, the photometry type that I'm plotting. So I change to the automatic reductions or something like that. And then I can zoom in on part of the light curve, and I can start looking at things individually to start making scientific decisions. I can say, do we have enough data? We got a message in our Slack message today from Andy that said, we're not getting enough data on these two objects. Can we up our priority? We can do basic spectral analysis. We've implemented a line list plotting interface, which I'll show you here. And this was a 1A, and so I can put in a silicon line at 10,000 kilometers a second, and you can see that it matches up with the real features in the spectrum. So all of these are tools that can help us move forward in science. And so we need these automated type tools and these rapid tools to be able to even collect the data that we want. But not only do we need to do that, we need to do the next step. So once we have some of the data, we've made a decision. We've said, okay, this is a type 1A, but we need to actually say we need more follow-up data. So this is a different object. I can go directly schedule observations on a telescope from here. So with just a few clicks of a button at this point, so right here I've now got a list of exposures and how often I want it. And as I scroll down one more step, I can choose which proposal we get time on, and I click submit. And what that will do is that will submit a request to Las Cumbres Observatory. And then the telescopes at Las Cumbres will then collect the data. It will be processed by the archive. It'll be processed by the pipeline, which if you want to talk about pipelines, please let me know. I love talking about pipelines. The data gets sent back to the TOM, and then it will put it on that light curve. But it's not just Las Cumbres Observatory. This works on multiple observatories. And so this is, for example, say if I wanted to submit a request on Gemini, I can go back up here and say make a request for Gemini spectra. And as a few of observatories have realized that we need to start interacting as a group in a coordinated way, we've defined something called the Astronomical Event Observatory Network, AON. And what AON is it's a consortium of observatories that have agreed upon a way to set up APIs so that you can automatically trigger telescopes. Has anybody used the Gemini Phase 2? It's a little different than this page, if you've noticed. But because we've been able to wrap all of our logic in our own custom web page, we don't have to go through a lot of the problems and a lot of the other things to make Gemini, which makes Gemini so flexible. Okay. And instead, we're able to do it in a very fast and automated way. All right, so now you've collected a spectrum. Now we want a way to automatically be able to submit this information back to the community. I'm not going to talk much about this, but this is really just an advertisement for Andy's talk and Adam Brazier's talk as they talk about how we can communicate some of this information back to the community. So stay tuned for the HERMES talk. That'll be fun. And recently, we've also been able to generalize this to, say, non-localized events, where, say, a single RA and DEC doesn't describe the full event. And so we've done this in the particular case of multi-messenger with gravitational waves. And we've custom built this system so that we can start to do follow-up on gravitational wave sources. Let's see. So those were a couple of links. And so now we'll go, all of this is implemented in the TOM Toolkit now. And so we can go to, say, a detail page of one of these gravitational wave events, which hopefully loads quickly. There it goes. And again, you have all the data that you would really want about said gravitational wave event at your fingertips. You have a sky map that's ready to go. You have a list of all of the different GCNs associated with that. You also have targets associated with that. Say you find candidates in the gravitational wave area, detection area. You can automatically put that in your TOM, and so in this case what I would do is I'd click on this particular object, which this is just a dummy target, and with a few more clicks of a button, I can submit observations to try and get extra data on that candidate. Maybe that's to validate, to classify that candidate and say, oh, it's not actually a kilonova, it's a supernova. Maybe it's to get further follow-up and say, okay, how bright is the kilonova? Whatever you wanted to be able to do, you're able to do. All right. And finally, we've done our best to make this not a one-size-fits-all type solution. As we started working on this, it was very quickly realized that there are customizations that every science case needs to make. And so instead of making a one-size-fits-all, we built a toolkit with the building blocks for individual users to build their own TOM systems. And so I've got a couple of the links up here. Everything is open source. The documentation is quite good. So what this comes with is a flexible database at the center wrapped around Django. We've got several automated or already implemented connections to brokers like Antares and Lasser and Alerce, I think, are all in there. We've got observatory facility interfaces, so the ones that come default are the Aeon sources, but there's plenty of other ones out there. So, Gemini, SOAR, Las Cumbres. Several things to, get data to different users, things like that. Data visualization tools. Access permissions. Observing strategies. So, for example, cadencing. Keep trying to get data every night until you happen to get it, and then wait 3 nights, and then keep going, so that we can start to build those type of light curves that I showed you in the Global Supernova Project. We've also made sure that there is significant user support. So we've worked extensively on documentation. This is not just code that's said good luck. There's actually instructions, tutorials, and there's a Slack channel, plus we have virtual meetings from time to time. And so if you have questions, we would love to have you work with us. So yeah, I will end there and leave you with these TOMs are a really powerful way to move forward as we're observing, and we're really doing follow-up observations of the huge amount of transients that LSST is going to discover. And with the TOM Toolkit, we hope we provided the tools for you as users to be able to design your own and build the systems to meet whatever scientific needs you have. So thank you very much.
Thank you very much, Curtis, for this very nice tool. Any questions, comments? Go over here.
I have a more overarching question, and this might not be what the TOM is for, but is there a way to interact in a public and private way at the same time? Like, so if you wanted to say, I want the light curve to be public, outward facing, so that anyone can see it, like a TNS kind of thing, but still keep some data private while collecting it and all under one umbrella. Is that part of what a TOM can do, or is that a different thing?
Yeah, actually, we can do that. So there's a couple of ways we can do that. So every piece along the chain has a permission associated with it. So who can see an object is already, that could be turned on or off, so it could be public or not. If it's a public transient that's got some TNS name, you probably want that to be public. But then every individual data point has a permission associated with it as well. So you can say only this group can see these 5 light curve points, taken 10 seconds after explosion. And then everybody else, and then the rest of the light curve going forward could be public, and that's totally fine. Yeah. And so basically when a user logs in, they are only able to see the data that they have access to see.
Great. Any other question from
Back
the
there,
audience? Oh, I go here and then here.
Thanks, great talk. How performant is it for, LSST-like samples of hundreds of thousands?
It's not there yet, I would say. So our current database, we have about 250,000 supernovae in it. Or no, that's not, I'm sorry, that's too many, I'm sorry. 250,000 light curve points. Sorry, got to get the right unit there. They matter. We have several thousand objects in it, and that works just fine. At the level of LSST, when you're talking about hundreds of thousands of objects, things get a little bit scary. And that's one of our current future directions, is we're going to make sure that the performance scales to the full level we need to. In general, these are expected to be individual science groups, and so it's unlikely that any one group of a few people, a small number of PIs, is going to be able to deal with every supernova that LSST discovers, for example. Usually it's the ones that you're interested in on kind of a personal level. It's your 100 favorite or whatever, and then you can work on those more in depth.
That actually pivots into my question nicely. Do the TOMs operate in their own universes, or can you connect between them?
Yeah, that is an excellent question. Stay tuned for Andy's and
Okay.
Adam's talk, because that's exactly what we're thinking about as
Perfect,
well.
thank you.
Any other question from the room? You want one?
To your question, pay attention to elastic, because we're actually going to be loading up and eventually using a TOM as part of that. And hopefully we'll be able to answer some of the question you asked. We'll see.
Yeah, my hope is that, you know, the LSST Science Collaborations will all have a TOM of some kind to control their spectroscopic follow-up resources and things like that. That's the plan. So this is Gotham's plan. This is why he's like, you should give this talk.
Great. I don't see any questions on Zoom, so let's thanks Chris again.
Thanks.
And our next speaker